Thank you all for joining. Today I will tell you something about systems thinking. To have a good example, we're going to look at the pizza production line. You can see here a drawing of a pizza production line, but of course that's a little bit boring. So we have a little video to show you what this line looks like when it's in full production. Here it goes. Okay, so as you can see, it's a very large system. You can look at it as one large system, the pizza production line. But a system always has an input. So what is the input of a pizza production line? That's the ingredients that go in. And then, of course, also every system has an output. And the output in this case is frozen pizzas. And to make sure that it all operates, you also need some people around the line to make sure that everything is working correctly. So those are the operators that are running around the system. But such a system would be way too big to really start solving issues with. That's just too large to look at. So what we have done is, after a lot of talking and understanding what they're doing, is that we figured out where a very good piece was to start, and that was the cheese applicator. And the challenge there is that there's 9,000 pizzas that are going through the line per hour, and they're using tons of cheese. And cheese is the most expensive ingredient in a pizza. So what our game is to make sure that we are putting the right amount of cheese on a pizza to reduce giveaway. Because if you put more cheese on it than you want to put on it, then yeah, you're basically giving away your most expensive ingredient. But also you want to reduce the amount of operators that are running the system, because in that way you can also save money. So we really looked on the complete system, and we narrowed in on one of the cases that we could help with. That's currently where we're helping. So, but you can also look at this in a more structured and a more general way. So with the input of the system is the pizza base that's coming in with the sauce, as you could see in the video. Then we have the cheese applicator that throws over the cheese. And then out comes a cheese pizza. And to do that, you need some operators that also check if the quality of the pizza is right, and also if the right amount of cheese is on the pizza. So they look at what the outcome of the system is. And what we would normally do for a lot of our other customers, we would show them a dashboard and show them if this is right or not. But we actually want to go a step further. And to do that, you also need to look at what's going in, so the input side of the system. And the operators will try to turn on the knobs on the cheese applicator in such a way that the right amount of cheese is put on top. And they compare that to a defined quantity. This way of thinking about a system we can generalize. So we have an input, we have a system, an output. We have a regulator that tries to turn on the knobs on the system to make sure that the output is as expected according to a standard. So going back to the cheese example, that's again the same system, but we want to put some artificial intelligence in the middle to help us with setting the right quantities. But also you see that the world is much more complex, because there's a lot of effects around the system that have an impact on getting the right amount of cheese on the pizza. So it could be humidity of the factory. There's a cheese quality aspect, but also, for example, the camera system that we put in place to measure the amount of cheese also can have problems. It can have dust, lighting problems, dirt. So there's all kinds of things that we have to keep in mind to make sure that we can that the artificial intelligence can control the system in the right way. And to do that, we have to think about, we have to use new kinds of ways of talking about such a problem. And for example, we're using state diagrams there. So in this state diagram, you see 3 different phases: a startup phase, where we have to monitor what the perfect amount of cheese is. Then we have a regulate phase, where we have to control the cheese applicator in the right way. And there could be anomalies. And then if we zoom into the regulate part, there's also 3 states. So you can have no change when the amount of cheese on the pizza is perfect. But if there's a higher amount on the pizza, you want to decrease the speed of the cheese belt. And if that is back to normal again, you go to the no change state. And if there's a lower amount, you have to increase the speed, so there's a little bit more cheese falling onto the pizza. And that is where we want to put in this AI. And then also every state can be connected to another state of this state diagram. And for each state, you have to think, how do you get from one state to the next? So that's a different way of looking at our problems than we have done before. And another important thing is, as you already saw, there's a lot of complexity around the system. So you also have to think about what technique am I going to use to harness that complexity. So complexity eats complexity for lunch. And basically you have the complexity of the system and you need the complexity of a regulator, AI, for example. And there's some kind of linear line through that you have to match the complexity of the system with the complexity of the regulator AI. So for example, if you have a very simple system at home to regulate the temperature in your home with a Nest thing, you can do that quite easily with rule-based systems. But on the other end of the spectrum, you have cars like the Tesla that are self-driving, and you really need something complex to also harness the complexity of the environment of the car. So you need some deep neural networks to do that. And in between are all kinds of things that we are already doing at Itility. So we have the cheese case that I just explained, where we are doing some image processing and using rules. We have helped Cymer in the past to do gas refill of their big lasers that are used at ASML. And there we're using k-means clustering, which is a little bit more complex AI system. Then another example is at Amplion. We have done some license optimization and we used optimization heuristics for that. That again is a step up in complexity of the tools that we need because the complexity of the problem asks for it. And then finally, we're now working on seedling classification at the Verve, for example. And there we really need convolutional networks because there the task is really more complex than we've seen before. So this is going to be the game in the coming years. We really need to use all our knowledge that is in our backpack to make sure that we can match the complexity of the customer and solve their problems. And this is on any level. So we need cloud consultants, we need people building the software, we need a data scientist, and everyone together, we should build this system. So if I summarize, how do you become a systems thinker? Well, first you start with zooming out, looking wide, understanding our customer, understanding what their challenges are. So looking at the complete pizza line. But then when we have done that, we need to zoom in very much with that understanding. And we need to find a valuable opportunity where we can help that customer. And then we have to understand all the details. And when we do that, then we can start to design the system. And we need to match the complexity of the problem that we're trying to solve with all the knowledge and experience that we already have. And that then means that with the team that we're there, with all the backgrounds that we have, we use the right tools and the methods to solve the puzzle for the customer. And that's going to be the challenge over the coming years.